Hi folks, and welcome back to Physics with Captain Rod. I'm making this video here to go over some examples of how to do what I call motion studies here, where we're going to study the motion of various objects here. We're going to start with this first example here. Let's see, what does it say here? A car shown as moving at 40 miles per hour. The driver applies the brakes and the car stops in 8 seconds. Draw a velocity graph and calculate how far the car moved during that first 8 seconds. Work in meters and seconds. So let's start with this. All right, so this 40 mile per hour. First thing we're going to do is we're going to convert that to meter per second. So unit conversions. All right, so we got 40 mile per hour, which means mile over hour. And anytime you convert units, you are multiplying by a fraction. So I'm going to multiply this again by some fraction here. And we want the fraction to get rid of the units that we want gone and leave us with the units we want. So our fraction, we're going to want to have meters up top and miles in the bottom. And then you look up what's called a conversion factor. Now, turns out there are 1,609 meters in 1 mile. Now that fraction is now equal to 1. And if we multiply this out, you'll notice that the miles are going to reduce and leave us with meter per hour. Well, we want to get that down to meter per second, so we're going to multiply by another conversion factor. And we want to get rid of the hours, so it's going to have hours up top, seconds in the bottom. Then we look up the conversion factor for this, and there are 3,600 seconds in 1 hour, and hopefully we just know that. By the way, if you wanted to convert this to per minute first and then minutes to seconds, that's just fine. Or we can use this hour per second conversion factor to directly convert the minutes to or the hours to seconds. Now notice when we go through and we look at this dimensionally, the miles cancel, the hours cancel, and we're left with meters in the top, seconds in the bottom. And if we multiply this out, I believe what we're going to get is about 17 meter per second. All right. Now we can start analyzing the motion of the car. Now, I'm going to start with kind of the motion diagram for the car. And again, what you want to think of is like snapshots in time, like a digital camera taking photos. Click, 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 and superimposing them. I'm going to represent or use just a dot to represent the car. So the first delta t, the car's, it's moving relatively fast. We're going to have a fairly decent delta x. But again, the driver is applying the brakes, so the car's slowing. So the delta x's are going to get smaller and smaller and smaller until eventually the car stops. And again, these dots are representing the car. Now, when you start studying the motion of an object, we're talking about the relationship between position, velocity, and acceleration. So, all right, position here. How are we going to measure that? So what I'm going to do is define a coordinate system. I'm going to put it right here. Call this the positive x direction. Now, you can put a y-axis on if you want, but it's a one-dimensional problem. All right, so now position is what I'm calling x. And also notice I put the coordinate system origin so that at t equals 0, like when we start this problem, if you will, the x coordinate is 0. Now, you don't have to do that, but there's really no reason to work it any other way right now. All right, and all right, now we're going to move on here. Now, when you're trying to study the motion of an object, I always recommend this. Velocity graphs are wonderful things here. So I already put an axis here for us. So I'm going to come down here and sketch this here. So this is going to be velocity against time. Now at t equals 0, our car is moving at 17 meter per second. So I'm going to go ahead and just put a point on the graph here and put 17, and I'll just put the units over here, meter per second. Now, the driver hits the brakes and the car stops 8 seconds later. So 8 seconds later, I'm just going to put this over here somewhere. And the velocity is 0. So this coordinate right here, this is the point 0, 17 meter per second. And that's actually 0 seconds, 17 meter per second. The coordinate to this point on our graph here is 8 seconds and 0 meter per second. Now the million-dollar question is, how do these connect? Now, in reality, these probably look, you know, maybe something like this. There is probably some curvature here. One of the reasons why there'd be some curvature, so air drag is speed dependent. And early in this trip here, like when the brakes are first applied, air drag is probably a larger factor than the second half. And just because of the nature of the force on the car and the directions, I think that would give us a curve that's slightly concave up. The actual curve, not important. What we're going to do here is we are going to assume a linear relationship. It's very common to approximate, curves that are, you know, close to linear with one which we're going to say is actually linear here. So we're going to assume that that is a straight line. So I'm going to put assume linear. Physically, what that means, you'll notice that if this is straight, that means this has constant slope. So what we're saying here is we are assuming that our acceleration is constant. And that's a very common assumption for lots of these types of problems. Now, is it actually going to be perfectly constant in a perfect line? No. But the good news is this. It's going to be approximately linear. It is going to be pretty close to a constant acceleration assumption. We can make that assumption and have very little error introduced to our results. So that's a pretty common thing to do in physics. All right. Now let's talk about this graph and how we're going to use it. Well, hopefully you've seen my video on how to use velocity graphs to calculate displacements. The delta x for the car we can get from this area under this curve here. And that's a triangular area. Area of a triangle is 1/2 base times height. So let's go ahead and just say 1/2. The base is 8 seconds. And then the height is 17 meters per second. And when we multiply this out, what do we get out of this here? Get about 68 meters. That's about how far that car is going to move while it's stopping. So in our picture here, that would be this. That's our delta x plus 68 meters. All right, now, although the question doesn't actually ask for it, I'm going to go ahead and calculate the acceleration anyway. Right, so our acceleration is change in velocity over change in time. And as far as this graph is concerned, what we're looking at is the slope. Now, when we compare this point to this point, notice the rise is -17, the run is 8. So what I'm going to do is just do it this way, minus 17 meters per second over 8 seconds. And I like decimals for these problems. That comes out to be about -2.3 meter per second per second. And if you want to write that as meter per second squared, that's perfectly fine. Now, a very important thing is, whoops, sorry about that. What does this minus sign mean here? This means to the left. Technically, what it means is opposite of what we call positive. Now, I've got plus x to the right. Opposite of that would be to the left. So there's this first problem worked out. I'm going to now scroll down on my handout here and let's chat about this one. So the car shown is moving at 40 miles per hour. The driver hits the gas, right, as opposed to the brakes, and the car's speed increases to 70 miles per hour in an 8-second time frame. So as far as how do we work this, basically the same way. First of all, let's get the units nice and consistent. All right, so the 40 mile per hour, which is mile over hour, we've already done that, and that came out to be, I'm going to have to just look at my deal here, 17 meters per second. Next thing is the 70 mile per hour. And what I'm going to do to keep this video as short as possible, I'm going to assume that you if you're watching this, that you can get that converted. That comes out to be about 31 meters per second. All right, same method as before. Similar to before, we're going to define a set of coordinates here. So let's go ahead and do this. Let's call this the positive x direction. Motion diagram, fairly important. Now at t equals 0, the x coordinate is 0, but the car's moving at 17 meters per second. So when we draw this motion diagram, right, we're going to use the dots to represent the car. So there's my first delta t. And there's my delta x here. Change in position. During the next one, however, this car's speeding up, so the next delta x is going to be a little bit larger. Then the next delta x a little bit larger than that. So this is how we would show that in our diagram. All right, the velocity of the car would be increasing. So I'm going to go ahead and put a velocity vector there. There's our 17 meter per second. But sometime later, it's going to be a little larger. And then again over here, it's going to be that very last one here is going to be the 31 meter per second. All right, so when we draw our velocity graph now, velocity against time, at t equals 0, oops, car's moving at 17 meter per second, so I'm just going to put the units off to the left. All right, so we'll put that 17 meter per second here. Again, where you put this, not really important. This is just kind of a rough sketch to kind of lead our work here. But once we do that, we've kind of made a scale. So if this distance is 17, 34 is roughly twice that. 31 is a little bit lower, maybe about here. So again, 8 seconds. Doesn't really matter how far over we go. But now we've kind of set a scale. 4 would be about here, 10 about here, and so forth. 31 meter per second is looking something like this. So this would be the point 8 seconds, 31 meter per second. Just like before, we're going to assume constant acceleration, which allows us to connect those linearly. So acceleration equals constant is an assumption, which will allow us to move on with and make the math nice and easy. All right, so just like our previous problem, we can calculate the delta x by finding the area bound under this curve. That's this area right here. Now, this one is a trapezoid. So if you're not familiar with how to find the area of a trapezoid, I would just back out of this. I've got video series on how to find the area of a trapezoid. It's not too complicated, but it's basically, all right, you take the left plus right, divide by 2. That gives you this height to the center, and then times the width. So that's going to be 17 meter per second. I'm going to write the units last. Plus 31 meter per second. That's this distance on the graph. Over 2 times our width, which is 8 seconds. Now, I'm just going to write the units off to the side. The vertical components had units of meter per second. And the horizontal is times seconds. And that will work out to meters. You'll notice these reduce. And let's see, I get, if I work this out right, I end up with, give me just a moment here, 192 meters. Okay. And although it doesn't ask for it in the question, I think I'll go back and change this so that it does. Let's go ahead and calculate the acceleration of this car. And again, that's going to be a delta v over delta t. So when we go from this point to this point, let's get some color in here. The rise is this distance, and the run is this distance, right? So that distance on the graph there, that's going to be the 31 minus 17. I believe that's 14 meter per second. And then the run, that's this distance, that's the 8 seconds. So our rise is going to be plus 14 meter per second. I put that plus there for a reason. And the run, 8 seconds. And this comes out to be, let's see, what is that? What is that as a decimal? Give me a moment here. About 1.75. Positive 1.75 meter per second, or if you like, meter per second squared. The positive number here is indicating in the direction we're calling positive, so effectively this means to the right. All right, so that example done. Now, the video is at 14 minutes here, so I think what I'm going to do is just stop this here for now and just make another video for the next 2 problems. I like to try to keep these videos under 14 minutes, or under 15 minutes total, so hope you're enjoying this so far. Have a great day.